Yes, hello students. Now we are going to start the second unit of this course, and this second unit is based on uh, DC drives. As I discussed earlier also, that a drive in which the motors are DC motors are called DC drives. So, in this unit, we shall start with the different motors which are used in DC drives, then their characteristics, and then I will discuss starting of DC motors, braking of DC motors, then various conventional methods of speed control of DC motor, and then we shall finally discuss the rectifier control DC drive and chopper control DC drives. So these will be covered in this unit number 2. So let us first discuss what are the various motors which are used in DC drives. So here I will discuss only 5 motors which are commonly used in various DC drives. The first one I have listed here is separately excited DC motor. As the name suggests, you have separate excitation for armature and field. So this is armature, this is field. Both are given separate voltages. When they are separate circuits, you can have different voltages for armature as well as field. So you may design a motor with 230 volt armature circuit and 150 volt field circuit. So this is possible, and both can be controlled separately so that you can vary the field current keeping the armature voltage constant. So you can say that this field current which flows in the field winding of the machine, field winding is placed on the stator, armature winding is on the rotor. So on the stator poles we have winding, and here we can apply a voltage here, Vf. So current that flows here is equal to Vf upon Rf. Rf is the resistance of the field winding. So this will be constant if Vf is constant. This means that this flux, this If is constant, so the flux produced by this field winding phi will also be constant independent of the conditions which are prevailing in the armature circuit. What will be the voltage, what will be the current, and this armature current, of course it depends on load on the motor. If the load varies, Ia will vary, but the flux will remain constant. So this is what is known as separately excited DC motor. Second variation of this is the shunt motor, where the field winding is connected across the armature, shunted with the armature. So it is called shunt motor. So in shunt motor, again you can see that the armature voltage appears across the field winding. So they both have same voltage. So what is the current flowing in the field winding? It is V upon Rf, that is supply voltage upon the resistance of the field winding, and of course the voltage is constant. This will also be constant. If you vary the armature voltage to vary the speed of the motor, this will also vary. But at a constant voltage, this will remain constant, and flux will also remain constant irrespective of load on the motor. If the load varies, the armature current will vary. Armature current depends on torque on the motor. So armature current will vary. So as the load varies, Ia will vary, but the flux will remain constant. So here you can say that separate control of field and armature is not possible. If you want to vary the flux phi without changing the voltage here, the only way is that you can insert some resistance here, and by varying that resistance you can vary the current in the field winding, and therefore the flux produced by the field winding. So this is almost same as the separately excited DC motors. In the third variation is series motor, where the field winding is connected in series with the armature. And one thing you must remember that this current If is much smaller than the armature current. It is tried to keep If as low as possible, V upon Rf, so that the major power flows through the armature winding. So the resistance of the field winding when it is shunted across the armature should be high, whereas in series motor the field winding is connected in series with the armature, So this means that the current flowing through this winding will be high. It will be equal to armature current or it will be equal to line current. So the current carrying capability of the field winding will be higher here in series motor and much smaller in the case of shunt and self-electric excited DC motors. So here the windings used for the field winding will be of small diameter, thin conductors will be used, and to produce enough flux, large number of turns are required. So the shunt field winding will have thin conductors and a large number of turns, whereas in this case, because current is very high, the conductors used for the field winding will be thick, larger diameter, so that it can carry the current, and as the current is high, number of turns required to produce the desired flux will be less. So the series field winding will have a small number of turns of thick conductors. So here you can say that this armature current, same current flows to the field winding and same is the line current. In the shunt motor you have seen that line current will be equal to a summation of armature current and field current. Here line current is equal to field current and field current is equal to armature current. So the flux produced by this field winding will be proportional to field current and which is equal to armature current, and this is proportional to torque on the motor and the torque is equal to the load torque. So as the load varies, the flux of this winding will vary. So the DC series motor has produces a flux which is proportional to load on the motor. So at light load conditions, when the load is very low, then armature current will be tending to 0. This will imply that flux will be tending to 0 and that will mean that the motor speed will tend to infinity. So at low load conditions, the motor speed becomes dangerously high. So the use of series motor is avoided in the situation where the load on the motor may become very low. And if it is used there, then we must have some protective mechanism so that the motor is disconnected from supply as soon as the current rises or the current falls below certain minimum value or the speed rises above certain maximum value. Now this situation will be avoided if we are using a compound motor instead of series motor. So I have listed only cumulatively compounded motor because differentially compounded motors are not used. Because in that case the flux may become 0 because the two fluxes oppose each other, and again we can have the situation that is there in the series motor. So cumulatively compounded motors use two windings. One is connected in series with the armature and the other across the armature. So this is shunt field winding, series field winding. Current flowing through the field winding will be equal to IF is equal to V upon RF. RF is the resistance of this field winding, and this V, this voltage is almost equal to the supply voltage V. So this is almost same as supply voltage V minus some drop here that is negligible. So this is constant, whereas this current is summation of IA plus IF, and IA, as you know, it depends on torque on the motor, so it is load dependent. So as the load varies, IA will vary, and the line current, which is also the series field winding current, is summation of IA and IF. So as the load varies, the series field current will vary and the flux produced by this will also vary. They are so connected that their fluxes of the two windings aid each other. So the total flux is equal to phi SC plus phi SH. So as the load increases, the flux of the motor will increase, and if the load becomes 0, very close to 0, even in that case the series field flux will be very small, but shunt field flux will always be there, and because flux never tends to 0, speed of the motor will never tend to infinity. It will have certain safe speed. So this is an improvement over the series motor. So the characteristic of compound motor will be between series motor and shunt motor. Now the fifth type of motor which is used, sometimes used, is permanent magnet DC motors. Here, as the name suggests, we have a permanent magnet instead of electromagnet. That is, the poles are made of ferrite material, ferrite core, and the flux produced by the poles are constant. So you can have no control over the flux of this motor. So the characteristic will be identical to that of separately excited DC motor, where the voltage is kept constant. So they will have identical characteristics. The only difference is that the flux is not produced by the voltage applied here. It is fixed. It depends on the flux produced by the permanent magnet. So these are the 5 motors that can be used in DC drives. So now I will discuss the characteristic of the various motors, that is shunt motor, series motor and separately excited DC motors. Thank you for today.